Today we're going on to the next chapter in science, which is 4.1.6, and it's forces in fluids. So we are on page 218. Go ahead and read along with me. Forces in fluids. Objectives. Compare the effects of compression on a solid, a liquid, and a gas. Identify the relationship of force, pressure, and area in a fluid. Define Pascal's principle, and explain buoyant force. Some vocabulary. Buoyant force, the upward force exerted on objects in a fluid. Fluid, any substance that flows and takes the shape of its container. Hydraulic device, a device that uses liquids to transfer pressure from one point to another. Imagine spending the afternoon at the pool. You dive into the water, cleanly breaking through the surface. You challenge your friends to a race and swim several pool lengths. Then you all have a water fight, splashing water at each other and over the sides of the pool. You float on your back for a time, then you inflate a raft so you can float with less effort. You can swim, splash, and float in a pool because of the way the water molecules are created. Although the molecules in solids are bound together in a rigid structure so that the object does not readily change shape, it is not true of a liquid like water. Any substance that flows and takes the shape of its container is called a fluid. Both liquids and gases are considered fluids because their molecules move around more freely than the molecules in a solid. Forces acting on fluids have different effects than the same forces acting on solids. Compressing a solid changes the volume of that solid, but the change is so small that it generally is not noticeable because the molecules in solids are already so close together that they cannot be forced much closer together. When a liquid is compressed, the effects are transmitted to all parts of the liquid. You can squeeze a water bottle and all the water is affected. Most liquids, however, are not easily compressed into smaller volumes. Gases, on the other hand, can be compressed into a smaller space because the molecules are usually so far apart. The volume of a compressed gas is less than before it was compressed. Spray cans contain compressed gas that are pressurized to maintain the smaller volume. When the valve is open on a gas can, the air rushes out because the fluids are moving from area of high pressure to low pressure. When the pressurized air is released, the air carries the paint, sunscreen, cooking oil, or other added can contents and disperses it quickly. So if you look up at the top, Pascal's principle, we have a water bottle there. It says the force of the water bottle is the same at any given depth to the bottle. When the bottle is squeezed, the increase in pressure is evenly distributed throughout the liquid. Okay? If you think of gas can be, so gas in the air, if you think of water as its three states of matter, when water is a solid, all of the water molecules are really close and compact and they can't be squished down anymore, and so it creates a solid structure that holds its own shape regardless of the container that it's in. When that melts and becomes a fluid or a liquid, the molecules are now moving apart from each other and are rolling over each other in a fluid motion in order to still create something tangible but does not hold its own shape. It takes on whatever shape it is in the container. As that water then turns from a liquid to a gas, those molecules are moving even farther and farther apart, and it isn't something tangible that you can grab. Sometimes you can see it in steam or in clouds because it has moisture in it as well, but for the most part, it's not something tangible that you can grasp because the molecules are so far apart. Now, because the molecules are so far apart, you can condense the gas into a smaller area and kind of press it together. It's still going to stay in a gas form, but it'll compress together under really high pressure. So if you have a soda stream that makes carbonated water, you have a CO2 cartridge that carbonates your water, that is compressed CO2 within that bottle. When you press the button down, it shoots carbon dioxide really fast out of that bottle and into your water because it's under such high pressure. If you turn on your propane on your gas stove, or your gas grill, you can smell the propane, but that gas is being released into the air at a pretty rapid rate. And that's why they always say, like, don't throw aerosol cans into fires, because as gas expands, it explodes. And so the gas is moving really rapidly, and when it's put into a small container, it's under a lot of pressure. And the slightest release of it, whether it's a hole in the can or someone opening the valve, it shoots out at a very high rate, depending on how much pressure it's under. You can't really do that so much with water. You can only fit so much into the container, and it's not like you can pack it in even more. It holds its own structure enough that you can only fit a certain amount of volume. And so what they're saying, Pascal's law, is if you have a bottle of water and you're squeezing it, if you squeeze that bottle of water, it's dispersing that compression on all of the water, not just that one spot. And this is pretty tight, pretty stiff, so I can't really squeeze it too much, but you can see how that water just kind of disperses. If I were to squeeze hard enough, it'll eventually pop the top off, which I'm not going to do. So that pressure is the same throughout all of the water. Okay. Pressure is defined as force per area. The molecules and fluids are constantly bouncing around. When the molecules hit the walls of a container or hit an object in the fluid, they push against it. Imagine a fluid in a cylinder with a tight-fitting piston as a lid. The pressure is being exerted on the underside of the piston. The pressure being exerted on the underside of the piston is measured by how many times the molecules are bouncing against the surface. It can be expressed in the formula P equals F-A. P is the pressure being exerted by the molecules bumping against the piston. F is the total force of the piston, and A is the area of the piston. The units used to measure pressure in the metric system are pascals, named after a scientist. Okay, so unit of measure, like rather than saying grams or ounces, it's a pascal. Okay, so laws and principles on the side there. Laws and principles. The pressure on a fluid is equal to the force divided by the area. So pressure, P, equals, force divided by area. Force of a fluid can be increased by increasing the pressure on the area which it is distributed. So F equals P times A. So force is equal to pressure times the area. The density of a solid or fluid is the mass divided by the volume. So density equals mass divided by volume. Hydraulic devices. Hydraulic devices use liquids to transfer pressure from one point to another. A device called a hydraulic press is used to lift dentist chairs, hospital operating tables, and cars at repair shops. How does it work? A small force, such as a person's foot stepping on a pedal, is applied to a small piston at one point in the system. According to Pascal's principle, this small force affects all the fluid in the system and translates into a large force, F, at another point in the system, where there's a piston with a much larger area. The larger force is used to move the larger area like a dentist chair or an auto lift. How could the force of the piston be increased? The total force exerted depends not only on the pressure, but also the size of the area being hit by the molecules. Use the equation P equals F divided by A. Pressure equals force divided by area. The variables can be manipulated to solve for force. For example, force equals pressure times area. This means that total force can be increased by increasing the pressure, the area, or both. In the example, force can be increased by increasing the surface area of the piston or by increasing the pressure. Increasing the surface area can be achieved by using a wider cylinder. So there's some pictures on the side there, forces and fluids. So first, the molecules of a liquid or gas are compressed inside a cylinder of this piston. So a piston is like a rod that goes up and down. Cars have pistons. If you've watched the movie Cars, they talk about all pistons going at the same time, and it has to do with creating pressure or releasing pressure that is built up, that the gas, I don't know all the parts of a car or how it all works, but this is my understanding of it. And so gas is burned, the liquid gas is burned into a gas. The gasoline is turned from a liquid to a gas, and that pressure pushes the pistons and is what's powering the engine. And so those pistons are going up and down based off of the pressure within the engine. Okay, so in this case, you have a piston, you have the cylinder that the water's inside, and you have a piston that's putting pressure onto the liquid or a gas. So the molecules in the cylinder are not under much pressure when the piston is at the top. They have a lot of area to move around. The increase in molecules and temperature and the compression of the piston raise the pressure inside the cylinder. So as the piston goes down and compresses the space that the gas or the liquid molecules are in, it condenses it. And by adding heat, it said, by adding temperature and compression, it raises the pressure. The larger cylinder has more room for more molecules to bounce around according to the pressure in the piston. Okay. And then up at the top, you have a picture of a piston from the side. You have the input force with a small piston. You have the hydraulic fluid in the middle. And then you have a large piston pushing force outward. Okay? So if you think of it like a dentist chair, they have a little foot pedal that sends electricity or sends that piston, the smaller piston, into the hydraulic fluid that creates pressure, which pushes the larger piston, which pushes at a greater force, which can then do greater things. So from pushing that little pedal, they're able to lift an entire dentist chair up. Same thing with like at a car garage. If you've ever been with your parents when they brought their cars in for repair, they drive the car up onto a lift, and they have a lever for the hydraulic lift, and that hydraulic fluid creates pressure. When that piston is pulled, it creates a pressure, which then is pushed towards a larger piston, and that larger piston creates enough pressure to be able to lift a much heavier object, like a car. Okay. To increase the pressure, the molecules must hit the piston more often. This can happen in 3 ways. The first way is to increase the density of fluid in the cylinder by adding more molecules. More molecules bouncing against the piston increases the pressure. The second way is to increase the speed of the molecules. The faster the molecules travel, the more often they will bounce off the piston. Since the speed of molecules in an object is directly related to temperature, the hotter the molecules, the faster they move around. So increasing the pressure with this method means heating the molecules. The third way is to compress the fluid in a cylinder. This is done by pushing the piston down and squeezing the molecules together into a smaller volume. Because the piston is moving at the molecules as the molecules hit it, they bounce off faster than before. The same thing happens when a moving tennis racket contains a tennis ball, or contacts a tennis ball. The ball bounces off a moving racket with a faster speed than it bounced off a racket that is not moving. The moving racket has a greater velocity, which provides more momentum. So if you're just holding a tennis racket and a ball comes and hits it, it's just going to hit it and land on the ground right in front of you. But if that ball comes and hits it as you are swinging it, your momentum within the tennis racket is going to add, we read about this last time, that momentum is then compounded onto the other object and shoots it in the other direction with a greater force than it was coming at you. So it's like those two momentums are added together to create a greater force. And they use this as well within pistons, creating greater force. A greater number of molecules in a given space results in greater density. Consider the density of 2 common fluids. Water has a density of 1 gram per milliliter, or 1,000 grams per liter. Air has a much lower density, 1.29 grams per liter. Since water is so much more dense than air, the pressure exerted on an object as it travels down below the surface of water is much greater than the pressure under the blanket of air of the atmosphere. For example, the deeper a diver goes in the ocean, the greater the pressure. I'm sure you felt this if you've swam in a pool, especially like the Y pool gets pretty deep in the deep end. I don't know about you, but I used to be able to swim to the bottom, but I can't anymore because it creates such pressure in my ears that I can't do it. It hurts. But that's because the deeper you go in the water, the greater the water pressure is. And so for divers as well, if you think of deep sea divers who go down for hours at a time in really, really deep water, there's a lot of pressure on their body. For deep sea exploration, where you have submarines that go down, those submarines have to be able to withstand the pressure of the ocean to a great degree. And if the people were to get out of the submarine at that level, they would probably be crushed by the pressure of the water because there's such great pressure because it's so much deeper. And so with that, we've talked about this before with something that happens with divers when they come back up to the surface. You're going from a high amount of pressure on your body, and that pressure is lessening and lessening as you get closer to the surface. If you were to shoot straight up from a deep part of the water to the surface, you would get something called the bends. And what happens is the deeper you go in the water and with the pressure on your body, nitrogen in your body is distributed differently. And so if you go from a lot of pressure on your body to not a lot of pressure on your body, that nitrogen then disperses where it's not supposed to go, and typically it'll go into your joints. And so if you rapidly head to the surface, that nitrogen doesn't have time to reestablish itself in your body the way it's supposed to. And so you end up with pockets of nitrogen in your joints, and it's extremely painful. And usually you have to go into something called a depressurization chamber for long periods of time to help your body re-regulate that nitrogen out of your joints. And so divers have to come up at a very gradual pace in order for that pressure on their body being released to allow the working of their organs and the gases and fluids within their bodies to go back to the way it's supposed to go. Our bodies are not meant to be under heavy pressure like under the ocean. And so we've had to learn over years how to adjust in order to be able to explore and see the great depths of the ocean without harming our bodies. All right. What happens when additional pressure is exerted on a fluid? French scientist and mathematician Blaise Pascal determined that a change in pressure at any point in an enclosed fluid results in an equal change in pressure at all other points in the fluid. In other words, any additional pressure applied to a fluid is transferred in all directions throughout the fluid and even against the walls of the fluid container. This fact is known as Pascal's principle. If a person jumps off a high diving board into a pool, the pressure from the landing will be felt by all the people in the pool around the diver in every direction. Fluids exert a buoyant force on objects that are totally or partially submerged in them. Buoyant force is the upward force exerted on an object in a fluid. Since pressure is greater farther down a fluid, the force on the lower part of an object is greater than the force on the upper part. The result is an upward buoyant force. For example, an inflatable ball becomes more difficult to push down the deeper in the water it goes. At some point, the buoyant force becomes so strong that the ball flies up out of the water. The buoyant force pushes back with an equal and opposite force to the push. So if you, again, are in a pool and you have a raft or a beach ball, that beach ball will sit very happily on the top of the water, maybe a little portion of it under the water, but it's buoyant enough that it'll sit right on top and float. Now, if you were to take that ball and just pull it under, not all the way, but just a little bit, you can do it with a little bit of force, but not much. If you were to take that ball and jump on it and try and hold it under your belly and float on it, you're going to feel greater pressure because you're going deeper into the water. And the deeper it goes, the more pressure it is underneath it. And it's going to force that buoyant object back up to the surface. And so usually that's when if you jump on a ball, you roll to the side and it pops up, or pops up however it can to release that pressure because it's so buoyant. How is density related to buoyancy? First, the pressure exerted by a fluid, and therefore the force exerted by that pressure, depends on the density of the fluid. An object that is less dense than the fluid it is in will float. For example, styrofoam, which has a density less than that of water, floats on water. An object with the same density as the fluid is in hangs suspended within the fluid. An object that is more dense than the fluid it is in will sink. Furthermore, a fluid that is more dense than water, such as corn syrup, has a greater buoyant force. However, on the moon, where the gravitational force is less than that on Earth, the buoyant force is exerted by a fluid would also be less. And so you can see that within salad dressings sometimes. You get some things float to the surface. You get different layers of the liquids. That's because some have more buoyancy or density than others. And so the heavier or more dense liquid goes to the bottom, and the lighter ones go to the top. If you think of it too, there are other factors within a liquid that can cause something to be buoyant. So if you think of the Dead Sea, in the Middle East, it has an extremely high salt content. And because of that, salt causes things to be buoyant within them. So within our own oceans, you might float better in an ocean than you would in a pool or a lake because that salt helps keep you buoyant. Whereas in the Dead Sea, everybody can float pretty much level with the surface because the salt content is so high, it makes everything in it very buoyant. Buoyant force is the reason why some people with arthritis exercise in a swimming pool. Because the buoyant force of the water cancels out much of the force of gravity on their joints, they can exercise with less pain. Steel alloys have a density of 7.75 grams per centimeters cubed to 8.05 grams per centimeter cubed, which is 8 times more than the density of water. And yet ships are made of steel. How do huge freight ships float? The buoyant force is strong enough to keep them afloat because the overall volume of the steel changes when it's formed into a ship. A large part of the volume of the ship is made of air, so the total density is much less than the solid steel block at the same volume. The big ship displaces large amounts of water, and the weight of the water equals the buoyant force exerted on the ship. That's quite the scientific job to be able to, and mathematician for that matter, to be able to know the formula, how much can our ship weigh, how much volume does it have to equal the water pressure in order to keep it buoyant. That's a pretty important job when you've got a lot at stake with a huge ship. So if you were to melt down all of that metal, the steel within a ship, and drop it into the water, it would sink to the bottom because it's solid. But because that metal is pounded thin and is displaced over a large area of space and is full of air for the most part, it creates a buoyancy, even though it's made out of steel. If you were to have even a piece of, let's say, tinfoil, if you crumbled up a piece of tinfoil and put it into water, it would probably sink, or especially if it was heavy duty. But if you took that tinfoil and just laid it flat on the water, you could make sides on it and make a little boat, it's going to float because it has a larger surface area. And because it's not as dense as when it's crumpled up into a ball. It has more space for air in it, and therefore it floats. So some questions to answer for this chapter. Explain how compression affects a solid, a liquid, and a gas. How can the pressure of a certain gas be determined? What factors increase the force in a hydraulic device? Name 3 ways the pressure can be increased in a hydraulic device. What is Pascal's principle? And describe buoyant force. So go back into your chapter and see if you can answer those questions. Do your best to answer them. I would encourage you to see if you can find some videos that kind of give you examples of hydraulic presses, hydraulic engines, anything like that, so you can actually see one in motion and see it working. Or you can look up videos on buoyancy as well and see Pascal's law, any of that. Your lab for today, there's a couple different labs in here, but a lot of them do require materials. So as usual, if you have materials and would like to try them, great. If you don't, not a problem. So for lab 4.1.6a, buoyant force, how does the density of an object affect a buoyant force? You need a string, a lump of modeling clay, a Newton spring scale, which I'm pretty sure you probably don't have laying at home, but if you do, you can do this. A large beaker, marbles, and a mass scale. For 4.16b, you do not need a Newton scale, so you could do that one. And the next one you are not going to do because that has a lot of scientific materials that you probably don't have hanging around your house. So more so than doing the lab, I would encourage you to find some videos that are parent approved that would give you some examples of force on fluids. And we will meet again next time and going on to 4.17, flight.